Okay, guys, it's Mr. Race here to help you out on the second part of the 3-2-1 activity. What we're going to be doing is looking at some data cleansing using Python. So the temperature file that we had before was really nice and clean. So if we look at all those, there was no missing values, no incomplete records, so you didn't require any data cleansing at all. So depending on how the data is collected, it may not be uniform and need to be cleaned. For example, you could collect the temperature data from people across the country. They might have entered in with different abbreviations or spelling or capitalizations or just different things throughout the way. So in this section, we're going to learn how to use the pandas function to help clean the Python or clean the data in Python. So what we got here is the carbon dioxide in the air can increase due to human activities such as like deforestation or burning fossil fuels and other natural processes such as respiration of volcanic eruptions too. Those change things. So what we're going to use is Python to clean and analyze the CO2 data collected from over several decades. So we're going to observe the contents in the or CO2 data CSV file that we've downloaded or that's attached to this here. So we got this. All right, so basically we're going to look at this and see what unit of measure the CO2 average for, oh wait, what is the unit of measure for the CO2 average and what does it stand for? So pretty simple question right there for you guys, but make sure you can read through this here. The average CO2 is expressed by parts per million or ppm, all right, which is the number of molecules of CO2 in every 1 million. Okay, so molecules of dried air that are vaporized. So we got a million of them. How many of the million molecules are CO2 molecules? Okay. So what do you think the column decimal year stands for? So let's see, we got year, we got month, which is right here, and then right here, decimal year, and then average. What do you guys think that decimal year stands for? Well, take a look at it. We know that the year is 1958 and it's the third month. So the decimal year, if there's 3 out of the 12, right? You can go ahead. Is that 3/12 of the way through there? Well, 3/12, that's 1/4, so not quite. All right, 4, 5. All right, so that's 5 is 1/8. 6. Okay. Take a second, maybe look through your problems here, see if you guys can think about what that represents. Okay. So you think about it, yeah, a full month would be 3, but maybe that is like how many days, right? Because full month, like if we're talking about March here, which would be just over 2. So 2/12 would be 1/6, which is 0.166, and 3 full months would be 1/4, 0.25. So this would be like what day we're looking at here. So specifically what day of the year. So the further along we go, we can see 12 would be 0.9. So that's right towards the end of the year. And that kind of makes more sense. So the decimal year basically is the decimal approximation of like how far through that year we've gone. So on January 1st, 1958, that'd be 1958.000. All right. And then you can see probably December 31st would be like 1958 would be 1958.999. Okay. What do the values -999 and -1 mean? Okay. So you have to look up here. Basically, -999 means that the missing months are denoted by -99. So we don't have the months for that part here. So 3, 4, 5. We don't have June here. There's no measurement. And the -1 means no data on the number of days. So we don't have any of the number of days, which we don't really have any of them, do we? Oh, okay. Now we get some more. So some of that information is not really given to us. All right. So what we're going to do is we're going to create a new Python file, okay, in the same folder that has these data. So if you want to go through, what I would do here is to, fork this off here, make sure that this is part 2. Okay, you can call this main file, well, we're going to call this the CO2 analysis, but we're going to make sure we go through this here. So we can take all this old stuff here that we did before and we can get rid of this. Oh, actually, no, we don't want to do all that quite yet. All right, we're going to reuse the code from the temperature analysis program that we have here. And we're going to try to read the CO2 file and store in a data frame known as CO2 data. So let's go through and maybe get rid of all this stuff here, anything below. We might need it, but we might not. We can always go back to our old folder that we forked and get that. So we want to call this CO2 data. So we're going to change CO2 data, and we're going to read the, make sure we get this right here, CO2 data.csv. And it already predicts it there. Okay. So I'm just going to run this, make sure that this kind of reads it and don't get an error. There we go. All right. So now what we're going to do, you know what? Control Z. I'm going to redo that. I'm going to leave this stuff here, but because we want to go through and make a line graph like we did before. So yeah. CO2 data. You know what? I wonder if I could just do this. No, we'll do it all together. I was going to have one at the same time. CO2 data. CO2 data. CSV. Okay. So what we want to do is to plot the averages on a line graph. So what column should we use in here for our line, for our averages? So you want to think about here, which one should be our x-axis? That should be the year, right? Okay, which column should be our y? Index 3. Okay, so let's go through. We're going to make our x and y. Oh, okay, hold on 1 second. Got another kid bot. Okay, so sorry, let's get back to this. So we want to figure out what we want our x-axis to be. Our x-axis should be like our decimal year. We could just use year, but that'd be every single one would be the exact same. We want to have the decimal year here to represent each one, because you can see the average does change throughout the year. And so we're going to go through this. So we're going to, x-axis is going to be the decimal year, and we're going to make sure we use the exact same wording here, decimal year. All right. Actually, was there anything else we need to do here? Change the header? No, maybe. We'll find out. And then what we want to do as our y-axis, we want our average to be there. So let's do like what we did with our code here. Go to our main code here. We're going to plot, but we're going to not use the temp data here. We're going to use the CO2 data, and we're going to use the decimal year. And then we're going to use the CO2 data. And we are going to use the average, which I believe is capitalized. And so this is where we just want to double check that decimal year all lowercase with the space, average is capitalized. Okay. All right, and we probably could change the labels here. The Y label, we can make it just say average PP parts per million. The Y, we can say years, and the title, we can put what's this data over again? Look here, this is the average expects. Yeah, which I'm just going to copy that in there because I'm kind of lazy. Okay, so what I'm going to do is I'm going to get rid of everything except for the plt.show. And let's see how well this runs. So I'm going to full screen this here to make this look a little bit better. Make this graph even bigger. All right, okay, first I got a thing that says key error decimal year. All right, did I spell it wrong? Yeah, decimal year. I'm going to just copy that here. Copy. And then I'm going to paste it in there just to make sure I didn't spell anything wrong. Look the same. See, we get the same error. Okay, here's the other thing here. Our header here, our header row. In our temperature data, our header row was element 0, right? But in the CO2 data, we have some information before. Well, we can either get rid of this information or say that our header should be at header number 5. So let's change the header. Let's see if that works. So now it's going to look at the header, find out which one says decimal year. And there we go. Okay. So if we can see our parts per million graph, we definitely have some jumps in here. It doesn't look great, but we can kind of see the natural trend of what's going on here. Okay, so basically we get a line graph, and we get something similar to this one here. Actually, did we plot a line graph? Yeah, we did. Ours just look, there's one that has a little bit more graphs. I guess we can change the view of it a little bit here. So why does the line have huge dips to -100, and what should we do about those? So if you think about those, that goes back to our data here. I keep clicking the wrong one here. But in our data sets, we have these -999. Remember, those are just missing values. So somebody in 1958, sometime in June, didn't record the average part. So that information is just gone. It wasn't saved. Same thing in here. So we should probably get rid of those things, or maybe calculate an average close to it. So we could just either get rid of that information or change that data to represent maybe something in between. So there's definitely different ways that we can clean the data files. Instead of like manually going through and deleting every single one of the rows, we can update our Python code to remove those rows from the data frame. So we could just get rid of that information too. So what we're going to do is add a line of code to the existing statement to import the math module. So any import here, we're going to do that. So we're going to import math. Import error. That's weird. Okay. So next, what we're going to do is we're going to insert the following code segment after we load the data frame object, the CO2 data. So after we got that right here, we're going to insert this code. Copy, paste. So CO2 average equals CO2 data average, replace 0.999 with math non. Okay, go through. So what do you think the first line of code is accomplishing here? So it's saying CO2 average. So it's going to make that row there, or that column, equal to CO2 average dot replace. We're going to look for any 999 with math non. Any idea what math non does? You can Google it, python.mathnon. All right, and non would be a not a number. That's what it stands for. So a not a number. It's just basically saying it's going to like eliminate it. Okay, next, there we go. What's the second line of code do? So the CO2 data dot drop NA subset. So subset equal average in place equals true. So what this is going to do is then going to drop the not numbers, okay? So there are different approaches between removing the rows from the data and replacing incorrect with a not a number object and calling the drop NA function as one. So what we're going to do is add 3 print CO2 lines as follows. So after the read call, the read CSV right here, we're going to do the call to view the data frame contents before any data cleansing is done. Okay, then what we're going to do is one after replace call. And let's see. So here's the read. Where's the replace call? Replace is right here. After that's done, we're going to add another print statement, and one after the drop NA to view the effect of dropping the rows. Okay, so let's see, let's run this, see if this works better, and then we can kind of see exactly what that print statement did. And this is where it's going to be kind of hard on Ripple to do. So it definitely looks nicer. We don't have those big drops, and the graph is actually organized because we only have a low that doesn't go down to -100. So if we wanted to do print CO2 average, Control C, Control V, and you know what? Maybe we can do input breaks before input, just to kind of make sure we see here, input, and then another one of those here. I'm going to clear this out here. And let's see, let's run this. Okay, so what we can see here, there's the first break. Here is the first one. We got 0, 1, 2, 3, and you can see on the third one, we got the -999. And we can go ahead, press enter now. Now what we did is we replaced that with a non, and then we can see press enter again. And we can see that one actually goes away. It goes 315, 317, 317.5, and then skips that one. And the next one is, and you can see there's no 3 here. It's just gone away. All right, so we can get rid of those here and clean up our code just a little bit. There we go. So that's what ends up happening. We end up getting our graph that looks nice and neat. Okay. Okay, so that's basically what we just saw. It goes through that raw data and goes through. All right, so once you guys get this done, make sure you guys submit this Ripple link here, and we're going to kind of talk about, what this all means here. So once you get yours done, go ahead, send in that Ripple link. Let's talk about what this means. So you should basically display or go to this website here, this NASA climate site here. And this should display a menu of options at the bottom of the screen. So each option represents a different site to a virtual sign of planet, basically. We're going to click on the global temperature here. Okay. We're going to look at this. How does this graph compare to the ones you generated in Python? So how does this look? Maybe you can say, look at the trends here to help you out. So can you go through here, and we can always zoom this out. So one trend that I notice here compared to our Python chart is that where's my Python code? Nope, wrong one. Did I close that Python already? I must have. Oh wait, no, I think it's right here. If we look at our average CO2 expressed per millions, it's definitely been going up from 1960 to 2020 and increasing, 20% or so. You can see, okay, 1960 to 2020 definitely got a steady increase as well. All right, so we can go through this here and we can press play and actually look at the effects from the 1800s. Let's kind of skip a little bit. I'm lazy. Let's look at 1960s going on. Definitely warmer than it was in the 1800s, according to this time series. Actually, it looks like it dipped a little cool in 1960s. Okay, 70s. Now start checking to see what happens here in any spots. Definitely lower there. Now America and other foreign countries in the 90s. Russia and America getting pretty hot. Going crazy over there in China and Alaska. Way hotter now up towards the top of the globe. Significant difference there. Okay, so definitely we can see a correlation there. So which year is the warmest year? What we're going to do is kind of look at this chart a little bit easier, and it looks like, well, 2020. I believe we're going to say 2016. Maybe 2020 might be a little higher. Yeah, 2016 or 2020. We'll put 2016 down. So basically, we can look at this. What conclusions can you draw about the global temperatures, the carbon dioxide amounts, and the climate based off of this that you've just attained? Okay, how can this data change in earlier years compared to the change in the more recent year? So you might want to go through and see, like, okay, what effects are going to happen, and then, is there anything we can do? Think about it. So go ahead, submit that, and when you guys get that done, we'll turn it in. So there's part 2, and we'll move on to the next activity tomorrow. You guys have a great day. I'll see you next time.